Nishant is there? Okay. So any question in your mind regarding whatever we have covered so far? What we discussed was, first we discussed performance evaluation. Of an existing or design. The building has been already designed. That is like analysis. Any design problem, analysis is integral part of design. First you have to do analysis. If you design RCC section also, you first learn how to analyze the RCC section. Okay. And once you understand that, you can use that to design the building. Okay. And second task which we are currently doing is design of a building. And when we say design, what does that mean? That means determining the sizes and the reinforcement in such a way that the building achieves a targeted performance. In general, this will be an iterative process. Every design is an iterative process. First we assume some sizes, then we determine the forces, try to determine the reinforcement. If the reinforcement is within acceptable limits, then those sizes are okay. Otherwise, we have to revise the sizes. Here, not only the sizes, we have to assume the reinforcement also to start. Then we perform nonlinear analysis, we calculate the performance. If the performance is acceptable, it is fine. Otherwise, we revise the sizes and the reinforcement alone. Now, for preliminary design, because these iterations, there you were doing iterations in terms of sizes only. Here you have to do iterations in terms of reinforcement also. So number of iterations may be large. So the iterations can be reduced by doing a preliminary design to reduce the number of iterations. And this method is direct displacement based design. But there is a problem in this method also. In this method, the performance level has to be defined. Two conditions I gave you yesterday. The performance levels are to be defined in terms of interstory drift. That is one requirement. So either you decide interstory drift or you determine interstory drift from the past literature, past experience, past studies. You determine the interstory drift corresponding to the performance level I or S or C, whatever you have chosen. Okay. So that is one requirement. What was the other requirement? So ductility capacity or the allowed ductility demand, okay, should be known. Ductility capacity is the total capacity till collapse. But we will not design our structures to utilize full ductility capacity. Okay, because in that case the damage will be large and there will be some chances of collapse. Collapse cannot be fully avoided. So what we do, we take a factor of safety. So in case of performance based design or displacement based design, the factor of safety is applied on ductility capacity. Okay, we allow ductility demand to be lower than the total ductility capacity. Okay, so there is the factor of safety. Factor of safety is not on forces. Okay, Contrary to force-based design, in force-based design, where the factor of safety is applied? On the forces. We increase forces, we reduce material capacity, we take characteristic capacity. Here what we have done? We have taken full earthquake force. Okay. We have considered expected strength, not even characteristic strength. Partial factors we have taken 1. So there is no factor of safety. But factor of safety we apply on the permissible plastic displacement. We do not take our building always up to collapse, because that is the maximum. And there is a possibility, some chances of the building getting collapsed, because our analysis is also uncertain. The forces we are calculating is also uncertain. In fact, uncertainties in earthquake are more than the dead load and live. So here also factor of safety is there, but that factor of safety is in the permissible ductility demand, okay, or the permissible plastic deformation, which we are allowing in our structure. Any question up till this point? Yes. How we decide new? Okay. So in reality, what we will do? We will plot the base shear versus delta rho curve, and here I will mark IO, LS and CP points. Okay. How I will mark? During the pushover analysis, wherever the first hinge is crossing IO, I will put that displacement as IO. And then what I will do? I will replace this by equivalent bilinear. This will give me delta Y. And then I will decide what performance level I want. Suppose I have decided that I want life safety performance level. So I will calculate the displacement corresponding to life safety. That is our target displacement. And the mu permissible is delta T divided by delta. This is for actual building. In real building we will do like that, but this curve should be known, isn't it? That means the building should be, details of the building should be available to me. But when I am designing a new building, what I will do? Based on the past experience, I will decide some interstory drift, let us say 1%, then life safety, let us say 2%, collapse prevention 4%, something like that I will decide based on past studies on similar buildings. Okay. So from here I will assume some interstory drift at which I am expecting to get life safety. But in my own building which I am designing, it may slightly vary. I may not get at the same interstory drift. So I will do a few iterations. Okay. So yes.
The main reason to give the interstory drift this limitation is the period effects.
Period effect is just one effect of interstory drift, but damage is also related to interstory drift.
Yes.
In a building, how much damage will occur, that can be quantified in terms of interstory drift.
Okay, but
the P delta effect is also occurring due to interstory drift, and that will cause additional displacement. That is one reason to control interstory drift. The other reason is, in case of performance-based design, the interstory drift is controlled to control the damage.
If the if we consider that P delta effect is the main reason to give this limitation to the interstory, I can find the delta for which the plastic hinge formation in the member is going to at what level, means if I consider maximum ductility.
We do not find from P delta effect. This is not from the point of view of P delta effect. These are from the point of view of damage. Okay. So P delta effect you will consider in your analysis. When you have plotted this curve, P delta effect has been considered there. So this curve has been plotted, capacity curve has been plotted, considering P delta effect. So P delta effect is already included in this. Okay, any other doubt? Yes?
What PB is you mentioned to be like
Initially it is elastic range and then it is going to be elastic range. So VB is varying. I do not get your question. Right? This is not your question. This is not your question. So what do you mean? So you mean here when I am doing, in fact when I am designing, almost invariably the building I am designing to go into elastic range. I never design for mu less than 1. So mu will be greater. Even when I am considering immediate occupancy, that is the best performance level we are targeting. So even here you can see that you get some value of mu. The displacement is greater than delta. So it will be in elastic range.
So this is the capacity curve
Capacity curve does not depend on earthquake. Capacity curve is characteristic of a building. This contains only building. I have not yet talked about hazard. I have not talked about response spectrum. Here it is building only. Okay. So this much is the displacement we are permitting. We have not yet calculated how much will be the displacement during actual earthquake. That is going to be our next step. At the moment we are talking about the building that under the given earthquake, this is the maximum displacement which I am going to permit. Okay, then I will see that whether the level of the hazard which I have chosen, under that the displacement is within this range or it is outside the range, or how should I proportion my building so that the displacement under that given earthquake is within this range. So let's see the steps. In the first case, when we are doing evaluation, what are the steps? Can you tell me? When we are doing performance evaluation, what are the steps? I want to do performance evaluation under a given earthquake. So what were our steps? Can you tell me? So first thing, we develop capacity curve. Okay. Then yes. We are talking about evaluation. Evaluation is for existing building. That means every information about the building is given. So we can develop capacity curve. That will be second. I will come to that. So we will utilize this for that purpose also. That's why I want to recapitulate these steps. That in evaluation what we are, suppose building was given to you. In that case, to estimate its performance, what will you do? Okay, reverse of that, we will do in design. Okay. So we will develop capacity curve. Then we have to obtain performance point. There are different methods of obtaining performance point under given earthquake. Let's use equivalent linearization because that we want to use in our DDVD. That's right. So what we do in DDVD? Sorry, in performance point evaluation. How will you evaluate performance point using equivalent linearization method? Not CMM, sorry, DMM, not constant ductility. If I want to use equivalent linearization, how I will go? Xi equivalent, how you will calculate Xi equivalent? For calculating Xi equivalent, what do you need? Mu. How will you get mu?
Capacity curve.
How? Let us say the capacity curve is this. How you are going to calculate mu?
We bilinearize this.
Bilinearize this.
Then
Okay.
Then
This is delta y. Then how I will obtain mu?
we fix our target displacement somewhere.
So you have to assume a target displacement. Okay. Assume target. For this assumed target displacement, you can calculate mu. Then you can calculate xi equivalent then calculate r xi and t equivalent. Okay. Once you calculate r xi and t equivalent, you can calculate St in elastic. Okay, from T equivalent and r xi equivalent, you will develop Sd versus T curve and corresponding to equivalent. You can read Sd in elastic. You can calculate delta T, that will be St elastic into gamma and phi. Then you will check let me call it as delta T2, and that assumed one was delta T1, the first time. Check if delta T2 is close to delta T1. If not, then you will go back to step 2 and you will continue till it is satisfied. You agree? You are all knowing the steps. I have only written those in a sequence. All of you agree with these steps? Now do the reverse of this. What Drashti was asking? What will be the steps? Get flew from here. What will be the step? Choose the performance level. Okay, and that will be in terms of delta T, the design or target displacement which is the maximum displacement you are going to permit in your building. Okay, so you will decide that. How you will decide it? As I told you that in terms of inter-story drift ratio, you can calculate. So inter-story drift ratio will be decided from performance level, and corresponding to that inter-story drift ratio, you can calculate delta T. Agree? Can you do that? Do not appear to be very sure. Do you need something for that? If I give you inter-story drift ratio, maximum inter-story drift ratio in a building, can you calculate design drift? Yes or no? Factor of? That is included. Delta D I have chosen sufficiently less than the ultimate. So factor of safety is already in delta D. Okay. So I don't know actually the ultimate. I know only that corresponding to IOLCP, these are the inter-story. How to get delta D from inter-story? Okay, let us say it is a 10-story building. Can you get delta D? Displacement upon height is inter-story drift. Agree? No. That is there only if the building deformed shape is linear. Otherwise, you need the deformed shape of the building also. Okay. So in case of low-rise buildings only, the deformed shape is linear. Okay. In case of tall buildings, the deformed shape will be, in case of taller buildings, not tall buildings, taller buildings, the deformed shape is going to be different. So Priestley has given inelastic deformed shape of buildings. So for buildings with number of stories less than 4, the deformed shape can be written as HI over HN. HI is the height at which you are calculating this delta, okay, and HN is the total. And for buildings having n greater than 4, delta I is given as 4 by 3 HI over HL into 1 minus HI over 4. So how will you calculate delta D? If this deformed shape is given and maximum inter-story drift is given. I want that inter-story drift anywhere in the building should not be more than, let us say, 2%. And for that I have to calculate delta D. How I will calculate? I can calculate. Here it is linear. If it is n less than 4, it is linear. So inter-story drift at each story will be same. So delta D will be simply inter-story drift ratio into HI, isn't it? But here you have to first obtain which story is having the maximum inter-story drift, and that you have to be. So from here you can calculate delta 1, delta 2, delta 3, delta 4, and then you can calculate, let us say here the inter-story drift is, let us say, maximum. So this is equal to 1% or 2%, whatever you have chosen. Okay, and then you can calculate, because when you will calculate the delta I, delta M here, okay, so this is giving you only the ratio, not the absolute value. So that you can calculate the absolute. This is giving only the deformed shape. Okay, so by equating this, you will get the absolute values of delta 1, delta 2, etc. Okay. Then, once you have calculated delta D, what will be the next step? We have chosen delta D. SD inelastic. How? From delta D, how I can calculate SD inelastic?
Delta T, which we get right now, upon gamma 1 5.
Right. So, second step, I will calculate SD inelastic, that is equal to this delta D, which I have chosen, divided by gamma 5. I will get gamma at 5 again from the deformed shape which I have given. Gamma and phi rho will be obtained from there. Agreed? Up till this point, all of you are with me or any difficulty? Then what will be the next step? Once you have calculated SD inelastic, what will be the next step? Yes?
T equivalent or hybrid.
T equivalent. How you will get T equivalent? From inelastic displacement. So SD, from SD inelastic, how to get T equivalent? What will you need? SD versus T graph. And SD versus T graph, will it depend on some parameter? For that, do you need something? Ductility. So you will require ductility demand. How you can calculate ductility demand? Either you assume based on past experience, or you calculate delta or SDY. SDY and delta y are related. Okay. How to calculate this? I will come. Okay, just wait till we complete these steps. I will tell you how to calculate delta y, but this is an important step where we have to calculate delta y or SDY for my structure. So you will see that most of this DDVD revolves around this calculation of delta y, because once I calculate delta y, delta d I have already decided, I can calculate mu. And once mu is known, what will be the next step? What will be the next step? Xi equivalent. Then after Xi equivalent, you calculate R. And once you know R, you can plot SD inelastic versus T equivalent curve. That is nothing but response spectrum divided by R psi. Then what will be the next step? Read T equivalent. Corresponding to SD inelastic which you have obtained above. Remaining steps I gave you yesterday. So can you tell me what will be the next step once we calculate T equivalent? Yes? K equivalent. How? M equivalent into omega square, that is 4 pi square divided by T equivalent. Then next step, we can calculate Vy. How much will be that?
K equivalent to the
Into delta D or SD in elastic.
Just be inelastic because this is the K equivalent.
This is very important. Okay. Delta D was of the building, and SD inelastic is the corresponding displacement of single degree freedom system. And here you have calculated K equivalent, not K. This is K of single degree freedom system. Okay. So Vy will be K equivalent into SD inelastic. Delta D and SD inelastic are related. Delta D is of the building and SD inelastic is of the single degree freedom system. So this stiffness is of the single degree freedom system or the building. Single degree freedom system. So displacement will also be multiplied for the single degree freedom system. And once this Vy is known, structure in our case is building. How we will design for Vy? In the same manner as we have designed for Vp bar. With the difference that in place of characteristic strength, we will use expected strength. Okay? And factors of safety we will take equal to 1.
Sir, again we reached to again force Vy, and for that we have to design.
Yeah, for that we have to design. And after designing, we will go to what I have written here and check the performance. You will design the building for Vy. You will get one design of the building. Once you have got one design, we are calling this preliminary design. It is not final design, preliminary design. So once you have done that preliminary design, you need to cross check that whether you have got the targeted performance or not, because you have assumed many things there. Here, now you can, based on that design, you can repeat it, okay, and check whether the targeted performance you have got or not. If not, you have to do further iteration. You could have used these iterations even without doing DDBD. But in that case, the number of iterations required may be very large. Okay.
Sir, this inter-story grid in first step we are choosing from fastest cylinder.
Inter-story drift.
We are selecting here is from fast pattern. What we
Right.
have.
Right.
But when I am designing the new plan or new building,
It may be different.
It may be different. But I didn't know that whatever I am going to design, if this is following which building.
That's why we are doing this stuff now. Here it will, here the actual inter-story drift will automatically come.
It means in this new building design, we are first making one existing building as a preliminary design.
See, for performance evaluation, the problem is that for performance evaluation, the building should be there.
Yes. So we are making one.
So first we are doing DDBD to get an approximate design of the building, preliminary design of the building. And then we are checking whether that our preliminary design is satisfying my performance requirement or not. Okay. Yes. Oh, don't say me that. Here, this SD inelastic, this we obtained here. So what is this? This is for earthquake, right? Response ऐसे versus T से तो बनाया है. So this, how this has been obtained from SA versus T, that is the response spectrum. And here also, we are calculating T equivalent corresponding to SDIM. From where? So this is the step where the earthquake, design earthquake is coming into picture. So we have SA versus T. Let us say I am doing it for MCE. So it is 1.5 jet, and then we have got this response spectrum. From here we calculate SD versus T. Then using RSI we calculate as the inelastic versus. Sorry. Overstrength factor is there when we have designed a building using conventional method, code-based method. So you can design, you have to design for BBY. Design for BBY can be done in two ways. One is what I have just told you, how to design for BBY. Okay. So one design is using expected strength and gamma equal to 1. That's how BBY is obtained. When we have obtained BBY for a given building, how we have obtained? Okay, so this was our BBD and this was our BBY. Okay, so this ratio is omega. We can obtain it directly. How we will obtain it directly? I have to use expected strength and partial factors of safety equal to 1. I can obtain this if I know VBD. Suppose I know VBD and omega, then I can also calculate VBY as omega into VBD. Same way, you can do the design also in two ways. One is designing directly, considering expected strength and gamma equal to 1, or alternatively, you obtain VBD as VBY over omega and then design as in case of code based. That means limit state design. I will be using characteristic strength and gamma as per the code. So either we can do this or we can do this. Which one is more accurate? First one. Why? Because there we are not depending on this capital omega. Okay, capital omega may vary from building to building. I need to know this for my building. Okay, so this is more accurate. If you know the exact correct value of omega, you can go for second as well.
So how to obtain overstrength factor for particular building?
Sorry?
How to obtain overstrength factor for particular building?
From capacity curve like this, I will design the building. From the design I will get BBD. I will perform the pushover analysis. Using expected strength and gamma equal to 1, I will get BBY, ratio of the two will be omega. That's why this is indirect method. The second one here is indirect method. Let's not go for that. Let's go for the first one.
But how can I get for BBD I have to develop the building for?
BBD, how can I get for my building? From the code. So BBD we can get from the code. Whenever you are designing a building, what is BBD? That same building, when you want to design from the code, you will calculate the shear, base shear, that is BBD. Here we are not using code, so we are obtaining VBY, then I have to use this value of omega.
So we are using the code for response spectrum.
Sorry?
Response spectrum we are using this code shape. From this spectral shape we are getting this data.
Right.
Then we are using it.
Right. So this you can obtain from code. We are designing for this response spectrum. This response spectrum may be from code. This response spectrum may be from site-specific analysis or from anywhere. So whatever this response spectrum is, whatever its shape is, the shape need not to be always like that. Shape may be a smooth shape also. So in that case, also you can plot this. So you will use the corresponding response spectrum. Okay, many times we calculate site-specific response spectrum. Many times we use the response spectrum given in the code. Procedure is valid for all response spectra, whatever way you have obtained. So what is the relationship between VBY of the single degree freedom system and the multi-story building? I am happy that you asked that. So this is the single degree freedom. This has M, okay, VB, what else? K. This has M equivalent, K equivalent, T, TE and T equivalent. And we have obtained this single degree freedom system in such a way that this VB versus delta rho curve is represented here. Here it is represented in terms of SA versus ST. So here you get T and here you get K. So this K equivalent you are obtaining from T. And this is your delta. Okay, this is SD. Yes. So we should not multiply by SD elastic. I told that wrong. Actually, it should be delta T, not SD. So K equivalent is not of single degree freedom system, it is of the delta. So it is delta. Please correct. Delta T will be slightly larger than ST. How much larger? Do you have an idea? It is simply gamma 1 into phi 1 2 into ST. What is the value of gamma 1 phi 1 2? I have told you. This is equal to C1 in DMN. How much is that? The typical value? 1.1 to 1.2. So this will be slightly higher. So this will give us base shear higher than what we have used previously. What we have been getting with ST.
Complex plane, so we never went from single degree freedom to multi-degree freedom.
We have gone to K equivalent when we are
K
calculating.
equivalent is for the single degree freedom.
Yes, but same is here also. That's what we have. That's why we developed this. The stiffness K equivalent of the single degree freedom system is same as this.
Stiffness and weight, mass of both these structures.
No, mass is not same. Mass is different. Mass of this
Okay, is the equivalent mass.
is equivalent. That is less.
Yes.
So mass is not same, but stiffness is same, such that the period comes out to be same. Single degree freedom system and multi degree freedom system, period, fundamental period comes out to be same. Because for same stiffness, if you are taking mass of multi degree freedom system will be larger than for the single degree freedom system, but that mass will be distributed. Okay, the K equivalent and distribution of mass and stiffness here is distributed. Here it is concentrated. So the two are such that the period is same. Period in fundamental mode, because this will have several periods. The period in fundamental mode is same as this single degree freedom system. Distribution of mass here is different. Distribution of mass here is concentrated. It is lumped at one point. Yes. Right. Yes, period is same. That's how, I mean, that's why this is equivalent. Why we say this is equivalent? So that the period is same and the inelastic behavior is represented like this. That SA is dB over M1 and SD is delta roof over gamma 1 phi. Then only if the periods are same, then only I can say that this is equal to the building. Actual building is multi-story. It will have different modes. So in the fundamental mode, period of this building is same as the period of the single degree freedom. Single degree freedom system will have only one period. Okay. So here we have to define a mode corresponding to which mode we are making the equivalent single degree freedom system. If I am making the single degree freedom system, equivalent single degree freedom system corresponding to the second mode, that is going to be different. Right. Okay. We have chosen it. Okay, for choosing that we don't use size. For determining the use size. Delta has come from endoscopic area. We have chosen an endoscopic area ratio and then using those deformed shapes which I have given you. So using these shapes, you have calculated delta. You know the peak in the story rate. So when there will be peak, this at any story where you are having maximum interstory drift ratio, if there the interstory drift ratio is let us say 3%, whatever peak interstory drift we have chosen, then at that time what will be at roof? That will be your delta. But not from here. Finally, why you are doing that ratio? That ratio you are doing because finally you are designing for VB bar. You have done an analysis. Analysis is giving you VB bar, but you don't want to design for VB bar. You want to VB. You want to actually want to design for VB bar. So what you do? Multiply everything by that ratio. So actually, what you are designing for VB bar, not for VB. Why we are doing that scaling? Okay. Although it is last semester's question, can anyone tell? This is a very important question, but last semester's question. Why we do VB bar by VB correction? Why we design for VB bar, not for VB in code-based method? This is very important. When we have performed analysis of our building, we have got some period. For that we have calculated base shear that we are calling VB. But we are not designing for VB. We are designing for VB bar, which is obtained from empirical period given in the code. Why that empirical period? We are giving so much preference. Is that so reliable? Is that so accurate? That our model is giving us, we have done a sophisticated computer analysis that is giving us a period and VB. We are not believing on that, we are believing on code. And we scale all our analysis with that base shear. Why? So it is based on empirical formula and we are doing the actual analysis. So why empirical formula is better than the actual analysis we have done? It is? Okay, so why upper bound is better? Upper bound is also a bound, not the real solution. So why upper bound? You have to keep in mind that the period of any building when you are calculating is uncertain. Okay, you are using some stiffness modifiers. Okay, those stiffness modifiers in different codes you will find different values. There is no unique value for those modifiers. So you will get different modifiers. There is uncertainty. And you have also seen when we were looking at the response of a single equilibrium system, actually the period changes during that. As the inelastic demand comes, it changes. So depending on the damage, the period is going to change. So period is not constant and there is lot of uncertainty. So whatever analysis you are doing and you are getting some period, there is uncertainty in the period itself. How to take that uncertainty into account? Your base shear, design base shear depends on the period. Your displacement, interstory drift ratio also depends on the period. So how we should design? And shape of our response spectrum is, that is also one important consideration. The shape of the response spectrum, SA versus T is like this, and SD versus T is like this. The period I have obtained here, this is uncertain. So what should I do? You can see here, this is the uncertainty, let us say. Here this is the uncertainty. So which value you will consider for force calculation? Force depends on SA, displacement depends on SD. So for SA calculation, you will consider this period, lower bound, and for displacement calculation, we will consider this period, upper, because of the shape of the response. Here lower bound period is giving you upper bound force. Okay, and here the upper bound period is giving you the upper bound displacement. So we consider both the periods, upper bound as well as lower bound. In our model, we are taking upper bound. By taking modification, disturbance modifiers, we consider only 0.3% of the beam stiffness. Okay, so that will happen when the beam has cracked, it has gone into an elastic range. So we consider our model is giving us this. And empirical formula is giving us this. So this will give us BB bar and this will give us BB. So displacement we calculate for BB. Forces we calculate for BB. So all our analysis we do for BB. But for the purpose of design, we increase all the forces, not the displacement, but all the forces by a ratio of forces multiplied by dV bar. What we have got from the model. Okay, so this is important. This is because the shape of the response spectra is such. If the shape was not such, suppose response spectra was flat for all period, then it doesn't matter. If SM was also increasing, then BB bar by BB was not required. In displacement, BB bar by BB is not required. That's why in displacement we don't do BB bar by BB. Yes. BB bar. Whenever you remember, you ask.
These time period you are considering lower bound and upper bound. But while designing structure, we are considering only one time period. We are not considering lower bound and upper bound.
We are considering because how you are calculating BB bar?
BB bar is analysis mode.
Which analysis?
Model analysis.
No. BB bar is not from model analysis. BB is from model analysis.
Oh, sorry. BB bar is from core.
Code formula.
Code formula.
You are considering code formula
Yes.
analysis period.
Yes.
That is upper bound. I mean lower bound. Lower bound period. This is coming from code. So lower bound period. Not BB bar is lower bound. Period is lower bound. Lower bound period is giving us upper bound base shape. Yes.
Considering this many uncertainties, how can we ensure our design?
Sorry?
By consideration of this many uncertainties, how can we ensure our design is valid?
See, wherever is uncertainty, engineers have to design, they have to live with uncertainty. Nothing is known precisely. Okay. Anything you take, even our concrete strength is not known precisely. Our steel reinforcement strength is not known precisely. Bearing capacity is not known precisely. Nothing is known precisely. Still, we have to make our buildings. So what we do? We take conservative. So whatever is conservative, we take that. So in some cases, the lower bound period is giving us conservative. So there we will consider lower bound period. In some cases, upper bound period is giving us conservative. There we will consider upper bound.
So you are saying that this is because of the shape of the spectra.
Right.
Then in all the philosophy of the design, considering from elastic to inelastic now, if you are considering, means I have to underestimate the strength and we overestimate the forces, and we have to check again for after designing this we have to check for the serviceability check, that is the displacement. When I am considering this in elastic design, these forces, they doesn't matter what is the shape of things.
It matters.
Because the design is
In elastic design, I mean this DDVD, which period we have considered? Lower bound or upper bound? Upper bound. Will it give us displacement on conservative side or non-conservative side? So we have already considered the conservative estimate of displacement here. Okay. And we are using that for our design. Because here our design is not based on force. The design is based on displacement. Okay. So that's why we don't need code formula here. Because we are not designing for forces. We are designing for displacement.
So, if we are designing for forces, why we are not taking directly VB bar itself? Because it is giving us a high force by dividing VB bar by that scale factor we are using.
Because it is already, what you have calculated is already upper bound. Why to multiply it by another factor?
Force based design.
Force based design we are doing, yes. But DDVT is not force based design. DDVT is displacement based design.
Design forces should be directly what we are what you are obtaining from VB bar itself. Why we are not doing that? I will calculate VB bar.
No. Okay, I got it. Let me explain this question to others also. First, you understand what he is trying to say. Finally, here also, we are designing for VY. Why not to take this from the code formula? Directly, that will be conservative.
because we are doing displacement based design. First we are selecting target, how much ductility I want in my structure, and from that ductility we are getting that V1. And in code what we
No, he is saying that finally you are getting forces, no?
yes, but that
Take these forces conservative.
these forces I am getting is based on my target displacement. And
Right.
whatever the forces code is given, that code doesn't know what is the target displacement. That is just understanding the strength of the material.
See, problem is this. Suppose I give you that design this beam for such interstory drift. Can you design? We don't know any method by which we can design the members, in which we can proportion the members for a given displacement. Okay, that method is not there. All our design methods are in terms of force. Finally, we need to know bending moment, axial force and shear force. So what we are doing, the target displacement, we are targeting a displacement only. That displacement we are converting into equivalent forces, so that we are able to proportion our numbers. But that doesn't mean that we are designing our building for a force. We are designing our building for displacement. Okay, but the design procedure which are available are in terms of force, in terms of strength. So we are converting that target displacement in terms of equivalent strength, or that strength which will give me that displacement. Okay, so these forces are not calculated based on the codal method, force based design. These are calculated based on displacement. That's why here we are not taking conservative design. We have already taken our displacement on conservative side. So that conservatism is already there. We need not to make another conservatism here. Okay.
So, in case of code,
Go ahead.
in case of code, so whatever the code is giving as multiplication factor for design these artificial structures, that code doesn't know when apply with that factor, that when earthquake will come, that the structure will go up to this, up to this, or up to this. That doesn't know. But in case of displacement design, we know that the structure will go up to this, and I want to permit displacement up to this, and then I will get one force which will design for I will that force for that force.
Right.
And that design force is this much. Whatever we are getting is V1.
Right.
And this force we are getting from the code applying the exponential reduction factor. that may be somewhere anywhere here, but that after designing for that course and where earthquake arise, that doesn't give me clarification that up to which point structure will go up to these or these or these. Is this
Yes, that's why we are saying that this method is better, because here we know how much displacement is actually going to occur in my structure and then what performance level I am going to achieve. But in case of code, we do not know how much actual displacement will occur, and at that displacement what performance level we are going to have. So that's why code based method is not adequate. That's from where we started this semester. The code based method was not adequate because we are not getting any idea whether my building will remain standing, it will collapse, or it will be major occupancy, or it will be life cycle. We don't know. That's why we are learning performance based. Yes. Doesn't matter. We are not designing for DVR. DVR has no meaning here. We are not considering any DVR. We are designing for this DVR. It is more because code DVR we do not know whether it is too conservative or it is unsafe. We don't know. So that serves no purpose for us. We will be designing for DVR only. No comparison with DVR. Yes, once we know DY and we will design. Okay, but this is not performance based design complete. What is incomplete? This is only preliminary design using DTVD. Performance based design will be complete when this is done. This is satisfied. Yes, this procedure is satisfied. Ultimately, you are getting the performance point which you want. This is an intermediate step. Calculating Vy is not performance based design. It is DDVD, direct displacement based design, which is used for initial proportioning of my building. Because the problem of performance based design is that I need a building to start with. So how to get that building? DDVD is serving that purpose. But don't think calculation of Vy is performance based design. Performance based design will be here. When I satisfy this, the targeted performance level, that is completion of performance. Yes. K equivalent we calculate like this. The relationship between K equivalent and T equivalent is like this. Okay, you tell me what is K of building? K of building. No, building is a multi-linear system. Multi-linear system. How do you obtain?
We have to plot the base year versus delta curve bilinearly and like here.
Multi-linear system, stiffness is a matrix. You can't get single value. Single value you get only when you convert this into equivalent single degree freedom system in a particular mode. So this K equivalent is, when we are talking about building, it is modalistic. Stiffness of building cannot be written like K equivalent. It has to be written in matrix form. Isn't it? For building, it will be always in a matrix form. When we are writing K equivalent, it means that we are writing corresponding to some mode. That means this is same as this. If you remember Rayleigh's quotient, what is 2 pi by T1 whole square? This is nothing but omega 1 square. What is this? Phi 1 transpose K phi divided by phi 1 transpose. Okay, this is n into n. This is 1 into n when we have put transpose, and this is n into 1. Okay, and this is also K1 star divided by M1 star. This is the mass in the first mode, this is the stiffness in the first mode. So our K equivalent is this, which is same as that of the single element. When you say stiffness of the building, you can't say like this. It has to be written in matrix form. When we are giving stiffness of building by a single quantity, scalar quantity, it means that we are talking of a mode. Then only we can say that. Yes.
K1 star, how it will be equal to K2?
How it will be equal to?
K2, as you see.
This is for elastic system. Okay. But this is representing the stiffness of elastic single degree freedom system. Do you agree? All this is for elastic system. Theory of vibration, whatever you have studied, is for elastic. So for elastic system, it will be like this. So if I plot Vb versus delta rho of elastic system, it will be like this. This will be my K, and in this case, this is Ke, and the corresponding single degree freedom system, M equivalent, okay, and the period is T, and I will plot SA versus SD. This will also be linear, and this will be T. Extend this to nonlinear system. In nonlinear system, what will happen? Initially it will be Ke, and then it will become flat. Similarly, this will be Te, this will become flat. So this is my K equivalent, and this is my T. Okay, so this is related with this. Okay?
Sir,
Yes.
stiffness is the property of the system.
Stiffness is property of the system.
When remote shape changes, how this K equivalent changes? Because mass equivalent we can understand. Because
So when you say stiffness is the property of the system, what do you mean by property of the system?
property of the system is what your term?
Let's take, let me take a simple building. Okay. In one case, I apply this force Q, and I will get displacement delta. I get Q versus delta. Then what I do? Same building. I apply Q here. Then also it will become delta. If I plot Q versus delta, will it be same?
No.
It will be different.
Yes.
Because the stiffness of a multi-degree freedom system, it is property of the system, but it depends on where you have applied force. Okay? And force is actually distributed. So distribution may also be different. I may apply like this, I may apply like this. Will it be same in the two cases?
No.
So it depends upon how we have distributed the force. Okay, that's why it is related to motion. Because force, if you are applying proportional to first mode shape, stiffness will be different. If you are applying force proportional to second mode shape, stiffness is going to be different. Yes. Through motion. We are not even doing this. We are going directly to this through motion. This is stiffness, spring and mass. Spring stiffness we will obtain phi transpose K phi, and mass we will obtain as phi transpose M. So mode shape relates. That's why it will vary from mode to mode. The equivalent single equilibrium system, the first mode will be different. Equivalent single equilibrium system, the second mode will be different, and so on. And you can easily understand that in first mode shape, you are applying the force like this, and total base shear and delta root. You are plotting base shear versus delta root. And in the second mode, you are applying the force like this. In which case you have to apply more force to get the same displacement. Or let us put it this way. I am applying acceleration. Okay, here the force will be acting like this. Here the force will be acting like this. To get the same displacement, in which case I have to apply more acceleration. Second case. So second case is stiffer compared to the first one. Higher modes are more stiffer. Higher modes are more difficult to excite. Higher modes require more energy to excite them. Okay. Higher modes have shorter period because the stiffness is more, the period becomes shorter. Higher modes also have a smaller mass. Okay. Mass participation goes on reduced in the higher. And in our pushover analysis, nonlinear static procedure, we are considering only the first mode. So we assume that first mode is enough. Higher modes we are ignoring. That is error. That is approximation. If you don't want that approximation, what you can do? In case of linear analysis, what we have done? We have done multi-mode analysis. You can do single mode. Single mode we call equivalent static, a linear static procedure. When we consider multi-mode, we call it mode superposition. Okay. Here what will you do? Mode superposition you can't do because superposition is no more valid in nonlinear system. Superposition is valid only in linear system. So you can't do more superposition. So what you are going to do?
SRS.
Hmm?
SRS is SRS is
SRSS is the mode superposition. SRSS and CQC are two methods of mode superposition. But those are not valid here. You can't do that. So what you are going to do? Times. So if you want to consider effect of all the modes, okay, you do not want to depend only on the first mode. You have to go for nonlinear time history analysis. Okay. So where you will consider your structure, subject it to ground motion. We are not converting it to any equivalent mode. We are analyzing the structure as a whole, and where it is subjected to, sometimes there will be a plastic hinge here, then sometime at some other instant there may be a plastic hinge here, at some other instant of time there may be plastic hinge here, and so on. And you will keep record of the maximum plastic deformation occurring at each hinge. Okay, that will give you the performance. The maximum plastic rotation occurring at any hinge, that will give you the performance of the wherever it is, because in IASC 41 the maximum rotation corresponding to IO, LS and CP are given.
Yes.
So you will keep record of the plastic rotation with different instants of time, and whatever is the maximum value, that you will check with the value given in ASC 40. Okay, so here multi-mode method is time history analysis. In nonlinear analysis, multi-mode method is time history analysis. Okay, because mode superposition is not valid. In superposition is not valid in nonlinear system. So if you recall how you have converted, now we are going into theory of biology. Our equation of motion was this was the equation. This is actually a coupled equation. You recall how did we convert into decoupled equations? What did we do? What trick we do? We multiply it by phi transpose, pre-multiply by phi transpose, post-multiply by. Okay, so then this will become diagonal. Why this becomes diagonal?
orthogonality of vectors.
Orthogonality of vectors. Because the eigenvectors are orthogonal to each other, so the cross term becomes 0 and only diagonal terms remain. Why the cross terms become 0 in orthogonal system? Physically, what does that mean? So what? Orthogonal. What does that mean? Orthogonal means perpendicular. Perpendicular means that if you are applying force in x direction and the displacement is y direction, what is the work done? 0. So if you are applying inertia force in one direction and the displacement is in the other direction, okay, so the force or work done will be 0. And phi transpose and phi, this is actually representing the work done. So it will happen to be 0 in when the non-diagonal terms you are given. Only one term will remain. Okay. So for this, for converting this multi-degree freedom system into equivalent single-degree freedom system, the prerequisite is this: phi matrix. How do you obtain phi matrix? Model analysis or For elastic, if stiffness matrix is constant, then you can perform eigenvalue solution. In our case, stiffness matrix itself is changed. It is function of x. So how you are going to obtain the eigenvalue? Eigenvalue. You can't do it. So in case of a nonlinear system, there is not single phi. The phi itself will go on changing. Okay. Eigenvectors will go on changing with analysis. So which eigenvectors you will be used here? That's why this superposition is not valid. We can't decompose this because one set will be valid at one value of k. Other value of k, it will not be valid. We will not get non-diagonal. We will get non-diagonal terms also. Okay, because phi vector, phi matrix is going to change with this case.
But sir, for time history analysis also, when you apply a quick data motion on this system,
We don't do this. We don't need phi. We take value of x at t equal to 0, then we get x t equal to 0.001, then we get, and this is the full vector we are getting, and then so on. We are not obtaining phi. We don't need phi.
While doing this time change, we need that. We can also give this eigenvectors. So it is giving only
It is giving eigenvectors only for the elastic. Eigenvectors are possible only for elastic. For inelastic structure, there is no unique eigenvector. If there is no unique stiffness matrix, how we can get unique eigenvectors? The stiffness matrix itself is changing. So our eigenvectors are also changing. So you have to do this at every instant of time. Then it is not working.
but sir,
Any method. Time integration you will need. There are so many methods of doing this. But what we are doing here, we are solving the full matrix, multi-degree freedom system equation of motion which is given in the matrix form. We are solving that directly. We are not doing any phi transpose and phi transformation.
no sir, but if I want to solve this equation by Newman beta method, there is algorithm, and in that algorithm I need some constant, and that constants are k equivalent, m equivalent, and these are phi by phi transpose m into
That is for single degree. So that is for elastic. Single degree freedom system solution. Okay. Mode superposition. You can do mode superposition using time history also. In case of linear system, there are two types of mode superposition possible. We convert this into equivalent single degree freedom system, and this ground motion I apply here. I solve equivalent single degree freedom system. Okay, for the same ground motion, and I get the response in there. And this response multiplied by the corresponding mode shape. And this multiplied by the corresponding mode shape of sorry. Okay, and the corresponding participation factor. I can do this, and when I add this together, I will get the response here. Okay, for this, I have to take this value, multiply by this, multiply by gamma. Okay, so like that, I can get this response. Okay, this is time history analysis using mode superposition. Alternatively, you don't do this. Analyze it directly. No conversion. Just like we are doing here. First x naught 0, then so this x vector, full vector, is solved. Here we have obtained this by adding these. Rather than adding these, I can solve it directly. So that is direct time history analysis. Alternatively, this is one method. Other method is direct time history analysis or direct time step integration. In nonlinear analysis, this is not valid. We have only this one. When our structure is going into inelastic range, nonlinear range, then this will not work. Okay. Some people have said that okay, it is not valid, but still we will apply. And let us see what they call it. Fast nonlinear analysis. FNA. Use mode superposition in nonlinear time history analysis. Even though it is not valid. Theory says it is not valid, हम फिर भी लगाते हैं. Okay. And then what interesting thing? In limited nonlinearity, suppose nonlinearity is limited in few members and you are talking about IOLS, you are not talking about colors. Okay. You will get very accurate results within no time. Quite accurate. Error is there, but the error is small. But when you are talking about colors, then this error is there. Then the results are gone. But if there is limited nonlinearity, so this method works well in case of limited nonlinearity. An advantage is with much smaller computer time. Solution of single degree freedom system even in nonlinear range is much easier. So they are performing nonlinear analysis only. Okay, so they are making equivalent nonlinear single degree freedom system. What is equivalent nonlinear single degree freedom system? Which we have just spoken. Okay. They apply the same time history and then add it using mode superposition as in case of linear elastic structure. And then they have obtained that this gives reasonably good results within no time. Time required is very less. So this is FNA. And e-test has this option also, FNA also, fast, non-human analysis also. This is the जबरदस्ती का मैटर. It is not valid, फिर भी हम करके देंगे. Okay, so I will stop here.
Sir, I have a doubt.
Please.
Sir, can we go to the previous slide?
Please.
Because we were talking about the IOLS and CP.
iOS.
And yes, sir. Yes, sir.
This one. Yes, sir. No.
Yes, sir. This one.
Huh?
With this diagram.
Okay.
So you were saying that by using that we will apply the time history. So we will measure the past equations and all, and we will calibrate that relationship with IOLS and CP with ASC. I have a doubt. Means ASC has measured that value, the past experience in their region.
No. The iOS CT has come from test reverse cyclic load test on components. It's not for building. It is for the columns and beams tested, and those columns and beams were tested world over, not in a particular, not only in one country. So there is what we call peer column database, peer or
Yes, sir, peer.
PRI, peer column database.
PER or peer
I
column
think it
database.
is ERI column database. So ERI column database what they get, because you have seen here also we are also doing testing. It is very costly. You can't do too many tests. So, but people have done this in different parts of the world. They combined everything, put together, and based on that, they have decided IOLSCP. So IOLSCP is not decided for a particular country, and it is not for a building. It is for mammoth, and based on the experimental test conducted on mammoths. Okay.
So are these limits are given somewhere else also apart from ASC?
Eurocode has given something. So if you look at Eurocode, something they are giving, but not in these terms. Those are given in terms of strain and some very complicated abstractions they have